Okay, so a little bit more of vector addition. This piece that we're doing is very procedural. So everything we did last time, doing again today. On the top, we only have 2 vectors, so it's just going to take a little less time, but we're doing the same steps. And so step 1, notice there's not really a prompt. There's no airplane or train. We don't know what's happening. So make up your own story. Like the one on the front, we've got newtons and newtons. If you don't know that's the unit of force, you will. Today we'll start talking about forces. We'll be dealing with newtons, not pounds, newtons, for the next month, okay? For the year, really. Forces are around the rest of the year. And so our story is whatever you want it to be. I've got 2 vectors given in the first picture. It says add in the components. We'll do that in a little bit. But we've got 44 newtons at 50 degrees below the positive x-axis, or you could say south of east, if you remember compass directions. And then 17 newtons is south of west. Actually, no, the way they have 70 degrees labeled, it's west of south, right? So who's V1, who's V2? It doesn't matter, okay? You can make whichever vector you want to be V1 and V2. And so I'm just going to kind of go in order here. I'm going to say 17 is my V1, leaving the 44 as V2. But wait a second, is this picture drawn at all to scale? Is 44 newtons really the same arrow length magnitude as 17? No. And so, you know, the spirit of estimation, 17, 20, 44, 40, right? And so I really should make my 44 at least a double length, right? And so I'm going to kind of draw it not to scale, but closer to scale. And this is going to be important whenever we do our tip to tail method in that blank space, the blank grid line. I'm going to draw these 2, tip to tail, and you really want to use as close to magnitude as you can, as close to scale. Now the angles, protractors are forbidden, so we'll kind of just estimate the angles as best we can. And then it says, what's the magnitude and direction? Just like the front side, page 1, we want the magnitude of that resultant vector, or if you want to say the resultant force. Resultant is the new vocab word. It just means what one vector takes the place of all the little vectors. So these 2 given, if I pulled them out and put 1 in, what would the resultant be, okay? And then the direction is the angle of the resultant. Now, I haven't drawn my resultant yet. It's coming. Now, to get those 2, we actually have to do the summation statements. Remember the Greek symbol, sum? We want to sum the horizontal vectors. And separately, because X, Y independence, we want to sum the vertical. And so I'm going to start with the sketch. The sketch is probably not something you'll have to do on the AP exam, but you might have to recognize a multiple choice question. Maybe they've got 4 different drawings and you have to pick out the right one, okay? And let me tell you, the wrong ones are going to make common mistakes. And so just because it's your answer doesn't mean it's the right answer. You want to make sure you know the tip to tail method and then how to draw in the resultant. And so I'm going to start with my V1. I'm just going to duplicate 17 newtons at 70 degrees. And so I'm just doing my best. There's V1. There's the 70 given. Now, could I use the complementary 20 degrees and do the math for complementary 20? Sure. But I like to just go with what's given. It makes students reading the keys. And when you look back, you're like, oh, I know where that 70 came from. It was given. And then I'm going to switch color. But now I want to kind of pick up that long 44 and put it at the tip of V1, okay? So again, I'm estimating, I'm trying to draw it kind of parallel. And it's okay if I go off grid. This is not to scale. And so maybe V2, tip to tail, looks something like this. And so we're drawing it more correctly with tip to tail method. Now, if you don't like it going off the grid, could we pick both of them up and just shift the initial position? Sure, nothing said we had to start at the origin. Just a nice place to start. But I could have started, at the top of the Y, and then I wouldn't have went off grid. But we're not making measurements on the grid, so it's okay. So now how do I draw in the resultant? Do I finish the cycle? Do I finish with tip to tail? No. What's the rule when drawing in the resultant? Who remembers? So I don't know if we talked about scenic route and shortcut, but if you do these two individual vectors, that's like the scenic route. What's the shortcut? The shortest distance between 2 points is from the start to the finish. It's a straight line, but make sure you know we're drawing arrows, vectors. If you draw straight lines, no points for you. If you draw arrows with the correct direction, so start to finish. And that's my resultant. Okay, so if this is two people fighting over something, a toy, if I've got kids, they fight over toys. And so they're pulling with 17 newtons and 44 newtons at respective angles. Well, if they were to pull together, what would the result be? Well, it's the one to take place of the two. That's your resultant, okay? And so we got to sum the individual components. And so if we go to the summation of vectors in the horizontal, it's going to be equal to V1x plus V2x. And then for the y, V1y plus V2y. So I need to find those four components for the two vectors. So for each one, I'm going to use the first picture to break up the components. And so 17 newtons, again, using 70 degrees, I'm going to come in and draw in. Now I know it doesn't make a perfect triangle. I'm just going to redraw it. That way I can draw it bigger. So V1, we got 17 newtons at 70 degrees. It's got V1y and V1x. And so how are we going to find each of those components? We got to do trig, right? And so let's do x first. What function are we going to use to find V1x? Sine. Don't get stuck in a rut thinking, oh, you always use cosine for the x component. Look at this. X is opposite 70 degrees. And so we're going to use sine. And so V1x will equal 17 newtons times sine 70. And make sure your calculator is in degree mode. Go on and punch it out. What do we get? A rounded, what'd y'all get? 16. Did you have a question? Logan? Was that a hand up? No, okay. So I get 16, and remember the components have the same unit as the original vector. Don't start, mixing up units. Well, we still need V1y. And so 17 newtons times what function? What side of the triangle is your y component? 70 is touching the y-axis, so it would be adjacent. So we'll use what function? Cosine. So cosine 70. Again, if you wanted to use the complementary 20 that touches the x-axis, then you would use cosine for x and sine for y. My practice is I use the angle given. And this one, I get 5.8. I'm going to keep 5.8. And so we can plug both of those components into the separate summation statements. Don't get them backwards. V1x. Think about one more thing. The x direction for V1, is it positive or negative? Negative. That 17 newtons is going west. And so that needs to be a negative 16. What about the y? Is it going up or down V1? It's going down. And so it needs to be negative as well. And so V1x is negative 16. V1y is negative 5.8. Everyone good with V1? Now, let's do V2. So V2, I think I can squeeze the quadrants in, the components in on that picture. And so we've got V2x and V2y. Notice the angle is touching the horizontal. So the horizontal component is adjacent and the vertical component is opposite. So that's kind of our old norm, right? And so to find V2x, we'll use cosine. So it's the 44 hypotenuse, cosine 50. Is this one going to be positive or negative? Positive. It's pointed to the right or east. And so 44 cosine 50, I get 28.3. And it's positive, we thought about it. V2y will be 44 sine 50. And should this one be positive or negative? Is it going up or down? Down, so it'll be negative. So at some point you have to think about direction. Okay, I would, just do it in the beginning, do it at the summation, either way, but you have to consider direction. And I get 33.7. And both of them are newtons. Everybody's newtons on this one. They both start out newtons, components, resultant, everybody is newtons. And so x with x, so negative 16 plus 28.3. And then on the y, negative 5.8 minus 33.7. Now we can sum the components. So 28.3 minus 16 is a positive 12.3 newtons. And then the two negatives added together, right? They are summed. I get 39.5, and they're both negative. Everybody good? We broke each vector up into two components, sum the horizontals, sum the vertical. Now, what did we just find? Who remembers from last time? Why do all this? What are we going towards? We're going to do Pythagorean theorem so that we can find the magnitude of the resultant, okay? And so these, if you will, are the components of the resultant. So over on the right-hand side, we said we're finding the magnitude of the resultant. Well, I know the components. Now here, I'm going to do something that a lot of students don't do, and sometimes they miss it. And if you just draw the components out, it'll help you see. So I have a positive x and a negative big Y. So I'm going to come over here. We had a positive 12.5, and then a big negative Y Notice I drew the components tip to tail. And then start to finish is your resultant, okay? It is going to be the sum of all those forces. This is our force in the horizontal, and this is our force in the vertical. Notice I switched over to an F rather than a V for vector. Today, we're starting forces, and so you're going to see that F net or net force, sum the forces. And so now we can do Pythagorean theorem. And what happens when you square a negative? It becomes positive. Save a keystroke, don't do it. Or if you want to put the negative in your calculator, use a parentheses. Okay, test it both ways. You'll get two different answers. And so 12.5 squared plus 39.5 squared equals that net force or resultant force squared. This is going to give us the magnitude. Oh, I put 12.5, it should be 12.3. Oopsies. Oh, one more. So 12.3 squared, and then square root, I get a resultant with a magnitude of 41.4 newtons. Everybody good with that? So if these were distances, you can either take the two long trips or you could take the shortcut. And so now for direction, which angle are they solving for? Well, it turns out most cases, they want you to find the angle from the origin, from wherever you started. Okay, so go back to that initial start point. This is where you're going to solve for your angle. Notice it's below the positive x. And so to solve for the angle, we got to do an inverse function because we're solving for angle. So you can pick your favorite, sine, cosine, tan. Tradition is to use tan, so I'm going to do that. Theta r is going to equal inverse tan. Opposite the way I have it drawn. It's not the only way you could draw it. I could have started with the vertical. But the way I have it drawn, it would be that 39.5. I did leave off the negative. Again, tan gets confused between quadrants 2 and 4 and 3 and 1. Hence why the drawing helps. And then adjacent would be the 12.3. And so plug it in. And I get about 73 degrees. Now, if I told you the treasure, if we go back to the treasure analogy, is it 73 degrees? Most people are not going to draw this picture out and they're just going to start digging in quadrant 1, right? 0 to 360, 73 degrees is in quadrant 1. So we got to be a little more detailed. It's 73 degrees below positive x. Or we could say 73 degrees south of east. Or what's another way? You could say, well, you let her in. Or you could say the negative 73, and it's implied that you go backwards, 360 minus, or you could literally, whatever 360 minus 73 is, what is that? 209 degrees, okay? So 209 degrees, everybody's digging in quadrant 4. Does this make sense? So you take the individual vectors, find their individual components, sum the x, sum the y. I redraw those components so I see what quadrant, so I see the angle that I'm finding, and then a Pythagorean theorem and inverse tan. It's very procedural. Questions, ask me a question about vectors. All right, so there's another one down below. And so I'm going to let y'all try that one another time. So independent practice, you have something to practice, okay? Now notice, I do want to warn you, they all look like all the arrows are the same length. Should they be? No, now they're all in the 200, so it's not going to be as drastic as the others we've seen, but 200 is the smallest, 276 is the biggest, and so maybe you want to draw this one a little bit bigger, 245 is somewhere in between, right? And so just watch the magnitudes. If you want to draw them tip to tail, here's some space to do so. And it's the same format, right? And so do the component breakdown, do Pythagorean, inverse tan. All right, let's transition to page 3 for forces. And so forces, I'm already recording. Before we draw the diagrams, we actually need to talk about what forces we have as like a list to choose from, if you will. But even before that, let's talk Newton's laws. And so before I write anything, and by the way, OneNote people, I'm going to be doing Newton's laws off here to the side. So if you have the paper copy, find some blank space, or maybe you have a notebook sheet. Okay, Newton's laws. I'm going to put my pencil down. Okay. You learned about forces and Newton's laws in middle school or something, right? So it's all about force. What's a force? Push or pull, that's it, right? So we have forces every single day. What is Newton's first law? Who can remember a few years ago, or maybe last year, what is Newton's first law? Yes. Unless acted on by, ooh, I love that you said unbalanced. You took the words out of my mouth. Usually students say, unless acted upon by an outside force, right? Does that literally mean outside? No. What does outside force mean? Well, it's forces beyond the object, right? External to the object or system. And so I'm going to rewrite it using the word unbalanced, because that's what really nitty-gritty we have. So the first law, an object in motion, or parentheses, maybe it's not moving at all, right? Maybe it's or at rest, stays in motion, parentheses, or at rest, unless acted upon by an, all caps, turn it on, unbalanced net force. That sigma that we've been seeing, we're going to start saying net force, net force, net force. You can also say sum of the forces, but chances are when you look at a single object, there's more than one force acting on it, okay? Right now, I'm standing here, you're sitting there. How many forces are acting on us? Not just one. We've got gravity. We all know gravity is pulling us, keeping us close to the ground, right? We're not floating away. Gravity is an external force due to the gravitational field of the Earth. It's pulling us down. But we're not going down, 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 down. The ground or the chair, the table, whatever is supporting us is pushing us back, right? Up. And so nobody has a net motion right now. Nobody has unbalanced. Oh, JP got up. Unbalanced, unbalanced. He's walking. Look at that. Okay. But for most of us, we're just keep doing what we're doing, right? We're at rest. We're going to stay at rest as long as our weight, our gravitational force, is being balanced by something else. Everybody good? So number one, first law is really about balance forces. You keep doing what you're doing. We all get the at rest, but let's talk motion. What if we were to go away, far, far away, outer space, where gravity doesn't work, right? We're going to have some kind of motion to get there. Well, if gravity quits working on us and nothing else is, can you describe that motion? Are we going to accelerate or keep doing what we're doing, constant velocity? Keep doing what you're doing. You only accelerate, there's only a change when something pushes or pulls you, right? And so I want to be a little more detailed in this one. So I'm going to add to it objects in motion. I'm going to add in constant velocity. So if the forces are balanced on an object that has constant velocity, I'm thinking of a car on cruise control, right? There's forces acting on the car constantly, but for them to be balanced, that's how you achieve constant velocity. And so they stay in constant velocity unless acted upon by an unbalanced net force. This is also called, so Newton's first law is also known as the law of, who knows it? Starts with an I, not an E. Inertia. Law of inertia. You keep doing what you're doing. And so it's the tendency to resist change. Okay. So we can recite it how we learned it years ago, but there's more little details to it. Okay. And we'll see it. I mean, especially on our force diagram sheet, I'll be identifying what each problem is referring to. Is it Newton's first law, second law, third law? Okay. But inertia is the tendency to keep doing what you're doing. Good deal? What about the second law? Who knows the second law? And don't Google. Some of you remember, at least take a shot at it. What is the second law? Yeah, it's the equation that we give forces, right? F equals ma. And so you've learned this equation, we plug and chug, it's a 3 number. Some of you are going to do a pyramid, which physics teachers hate, but anyway, not every equation has 3 variables, but anyway. So this is the equation we've learned. Now I want you to look at our College Board AP formula chart, find this equation for me. F equals ma. Is it on the formula chart? Kind of, sort of, it is. Look at the 4th equation down. It's written in terms of acceleration, and there's a reason for that. And so on the formula chart, it's written, one could say more accurately, the math is the same, but acceleration is directly related to that summation of forces, net force, and it's indirectly related to the mass. Notice I didn't just say A equals F over M. That's the same math. Newton's second law is really about the relationships, okay? Now, on the AP exam, are you going to have to recite or state any of these laws? No, but you're going to have to apply them, okay? And I've told you before, AP loves relationships. And so let's write these relationships out. So acceleration is directly proportional to the net force. And again, that Greek symbol just means sum of, where it's also called net force. I'll say both, okay? Eventually we'll just say net force. Now that there's a stipulation to that. Can I have all 3 variables changing? Good science, you just want to change one variable and hopefully see one other variable change, right? And so this is assuming there's a controlled mass, a constant mass. An example of this, what if I have two blocks, M and M? Maybe they're on some kind of surface, right? And so what if I push one of them with just F? Notice I'm not giving numbers. And then I push the other one with 2F. Who's going to change more? Who's going to accelerate more? The left or the right? The one on the right, right? And so this one will have more acceleration. Turns out it would be 2 if I have a factor of 1m, right? And then the one here on the left would have less acceleration, or just A. Direct relationship, double the force, double the acceleration. Well, what if you have a change in mass? So second example, I'll keep with boxes on the floor. We'll say the first one is M, but then what if I have a 2m? And so how does acceleration relate to mass? Well, if I have a constant force on this one, okay, so what if I push them both with just F? Who's going to accelerate more? Who's going to change more? M, the one on the left, the first one, right? So a smaller mass, you know this, you've pushed things. It's easier to move less massive objects, right? Lighter objects. If I told you I've got these two cars that stalled, right? And I need you to go push them. One's a little bitty Fiat smart car. The other is this big old pickup truck. Which one are you gonna move quicker first? Assuming you have the same force, you're gonna push the smart car, right? Okay. And so what kind of relationship is that? And so acceleration is indirectly related or proportional to mass. And again, that's assuming you have a constant force. You don't want all three changing. So that's really what Newton's second law is about, okay? Yeah, F equals ma. It's okay to write that. You'll see me write it in that order. But the way it's written on the formula chart isn't just to be mean. It's the force comes first. The mass comes first. Acceleration happens because of the force to mass ratio, okay? Now, I am going to do one more thing with that equation. We can find the unit, okay? And so the unit for force, let's kind of use maybe a little of this space here. And so let's talk units. What's the unit for mass? We've kind of talked about mass. You might think grams, but it's actually kilograms is the unit for mass. What's our unit for acceleration? Meters per second squared, okay? Now this is an acceptable unit for forces. So I could say I weigh whatever number, kilogram meter per second squared. But that's kind of weird. No one says that. We always say pounds, but guess what? Pounds is not SI unit. Does anyone know? And you've seen a preview. What's the SI unit for force? Newton, named after Fig Newton. Oh, Sir Isaac Newton. Yeah. Does anyone know a Fig Newton? It's a little cookie. Okay. And so it's a Newton. It's a derived unit. It takes the place of a kilogram meter per second squared. Okay. So you can have a force of 20 newtons. You don't have to worry about kilogram times meter per second squared. Now, I will tell you on the AP exam, whether it's multiple choice or free response, you are going to have to do some unit analysis. And so if they give you 4 different compiled units, maybe they say, what about kilogram meter squared per second? Notice what I just said, meter squared per second. Is that equal to a Newton? No. Okay. And so you got to know what it equates to so you can do those unit analysis. Okay. So there's units. I think that's it with Newton's second law. Questions on the second law? All right. Third law is what? Someone recite the third law. We've done inertia, objects at rest, stay at rest. We've done F equals ma. What did we learn about the third law? Right, for every action, there's an equal and opposite reaction, right? And that's the end of the story, and that's all we know, right? Okay, so let's write it out. For every action, by the way, what does action mean? For every action, what's an action? Well, acceleration happens because of a force. They're really saying for every force, and I'm going to go on and watch this, you'll understand at the end. For every action, a force on A, I'll explain as we go, there is an equal and opposite reaction. What does that mean? Another force. Stay with me. I'm going to say the force on B. For every action, for every force on object A, there is an equal and opposite reaction or force on B. And first, I'm going to show you a meme, and then we'll do the drawing, okay? Right now, you're not moving. You're not accelerating. Forces are balanced, right? We already identified those forces as gravity's pulling you down, the chair is pushing you up. Those are equal and opposite, yes? Do you agree? If they weren't equal, if your chair was weak and gravity wins, what happens to you? If gravity wins, you have a sore rear end because you fell down to the concrete ground, right? Okay, ouch. And so let me show you a meme, and I did not make this. Another physics teacher made this, and I loved it. Oh, here it comes. So I'm gonna give you a second. Do y'all know who the person is? Because only one person in fifth period did, and I was shocked. It's not Kanye West. That was another guess. Oh, Drake, okay. Today's 80s day, right? Hence the side ponytail, okay. No, it's 90s, but I'm used to like Dr. Dre. And so I always call it Dr. Dre and I'm wrong, but it's Drake, okay. Famous meme. Physics teacher got so tired of students thinking that every equal and opposite situation was an action-reaction pair, because on the AP exam, you're going to be tested on this, okay, some form or fashion. You're not going to have to write out Newton's third law, but you got to be able to apply it. The first two forces up above, they're equal and opposite direction. And then you see that little like geometry, is it congruency? I don't know. I'm just throwing out math words, but that little dash on both is indicating that they're equal. They're equal and opposite. That's you sitting in the chair. Gravity's pulling you down, and then Fn we'll get to later, but it's a normal force from your chair pushes you up. If you're not moving, equal and opposite. But Drake says, no. These are not an action-reaction pair. So what is? Remember I had force on A, force on B? I've got two objects. How many? Two. How many objects do you have up above? You sitting in the chair. Yeah, there's the chair, but these forces are on you, one object. But the force AB is two objects. I push on you, you push on me. I push on the chair pushes on me. I'm attracted to the earth, gravity. The earth is attracted to me. Whoa. How come I don't move the earth? The earth moves me, I don't move the earth, but if they're an equal and opposite reaction force, How come I don't move the earth? Mass. The earth wins, right? It's a much more massive, okay? I'm a much less massive. The earth can accelerate me more than I can accelerate the earth. Does that make sense? And so the bottom one, he says, yeah, now you got it. Your action-reaction pair, I have a pair of objects and a pair of forces. And look at how they're written. Force of B on A and force of A on B. You hear that reversibility? Okay. That tells us it's an action-reaction pair. That's your Newton's third law. The first example is an example of one of the laws, but it's not number 3. Okay, it's actually number 1. Go back to what Newton's first law was. For an object at rest, it remains at rest as long as the forces are balanced. So when forces balance on one object, it's Newton's first law. When you have 2 objects with equal forces on each other, it's Newton's third law. I'll be doing this a lot. You're going to hear it over and over again, okay? Don't miss this question on the May exam, okay? I promise they will test you on it. Okay, so I'm just going to redraw that picture in a way on the action-reaction pair. So note, you have a pair of objects. How many is a pair? 2 of objects. And they exert a force, equal and opposite, on each other. Okay. And so your picture, if we go with box A and then box B again, the force on A by B, and then the force on B by A. And I know you're going to read your textbook, right? Hint, hint, wink, wink. It's actually chapter 2 and 3. Forces is 2 chapters. It's so big. And so, you know, just baby steps, first 5-10 pages, whatever. You're going to see a lot of their force diagrams, their force labels with on and by, on and by. Prepositions are so important when you read the problem. Prepositions are going to tell you who to draw the diagram for, okay? Prepositions, on and by. Okay, so there's Newton's third law. We got all 3 laws now. It's not about reciting, it's about applying, okay? So that's what we're going to be doing after we give our list of forces. And so I'm going to go back up to the top. I think I can squeeze it in. And so now we're going to make a 2-column list. And I'm going to have a smaller column on the left. We can break down all forces into 2 headers. Field forces, which is caused by a field. These are non-contact. Contact. And then the other column, nothing fancy, they're just contact forces. So we could have put the header non-contact or contact, but field forces, so we've talked about the acceleration due to gravity. Well, that only happens if you're in a gravitational field. So what's this field? So I know y'all have watched some kind of sci-fi or fantasy type of movies, right? I'm thinking Hunger Games. I think it's the first movie, right? And is it PETA? He's walking through the woods and then Katniss goes, PETA, no. At the same moment that PETA does what? Touches the electric field. How do we know? Somehow she heard it. Can we hear gravity? No, okay. Maybe she saw it sparkle, right? Sometimes, or neon glow, right? Yoda glow or whatever. Can we see gravity? No. So you can't see and hear the fields, okay? Don't trust your science for movies, okay? But the only field that we cover in AP Physics 1, Well, it never had magnetism. They pulled out electricity. So the only field that we're going to deal with is gravitational. Okay? So this gravitational field is this invisible region around a planet or a being, right? Technically, you would have a gravitational field. It's just super, super like 20th decimal place, insignificant. But any planet, moon, whatever, has a gravitational field. It's this invisible, I can't see it, smell it, hear it, touch it. You can't touch gravity. But if another object comes into that field, what happens? It pulls you in, right? Gravity acts towards the center of that object. And so it exerts a force on a second object. Can gravity affect itself? Can the Earth exert a force on itself? Not in terms of gravitational field, okay? And so, gravitational force, that's our first force. Now, maybe you want to write out that word every single time, but in the picture I've already showed you, we just simplify it down to a symbol. And unfortunately, there's not just one symbol that the whole world can agree on. Heck, College Board can't even agree with itself, and I'll show you what I mean as we go. And so, if you want to symbolize it, I personally write a capital F, force, that's the variable, and then subscripts. Y'all know I love subscripts. They describe what that kind of force. So it's a gravitational force, Fg. Everybody good? Now there is an equation on your formula chart for F big G. That comes later. That's not this unit, okay? We're keeping gravity as a constant right now. The true story, you go far enough away, it's not constant. But for us in this classroom, gravity's constant. Now on the AP exam, or if you do AP daily, anything, AP progress checks, classroom, watch a YouTube video. I don't know what Khan Academy does. I don't know what Flip in Physics does. But even in our packet, okay, we use problems other people have made too. You'll also see a W. Any guesses what the W stands for? If you look on the formula chart, it stands for work. And that's energy that comes later, okay? The W that they're referring to is weight. What is weight? Mass, actually, yes, multiplied by gravity as a field, as an acceleration, not a subscript. And so a lot of people, even physics teachers, will commonly talk about mass and weight as if they're the same thing. But listen up, they're not. On the AP exam, if you say mass, you better mean mass. If you say weight, you better mean weight. Because if you mean the other one, and they're grading for the other one, you get it mixed up, you're losing points, okay? They are different. So let's talk, let's field trip to the moon. If we go to the moon today, okay, just imagine theoretical field trip, let's all go to the moon. We're gonna weigh less, right? We know that now. We're gonna weigh less. You stand on a bathroom scale, you're gonna weigh less. Do our clothes fit any differently? Pretend you're not wearing a spacesuit for survival. Pretend you can, you just have a mask of some kind of magic survival. But do our clothes fit any differently? No. Guess what doesn't change when you go to the moon? Mass. And so mass is all the particles that make you up. Weight is that mass, but then the gravitational effects on it. And so mass times the acceleration due to gravity is your weight, is force of gravity. I'm going to change that comma to an equals. It's all the same thing. And so when we go to diagram, I label Fg. If it's a force diagram, I make a force vector and I use a subscript. But if you put mg, that's fine. If you put a capital W, they'll know you mean weight, okay? Now what you can't symbolize it is just G. If you label a force as a G, that's not an acceptable symbol, okay? You're saying it's an acceleration. They want force, two different things. Good? Okay. And the unit, just like before, it's a Newton. We get our weight in pounds. By the way, just for reference, it's not 100%, I forget the decimal, but if you take your pounds and then times 4, you'll get your newtons, okay? 1 Newton is about 4 pounds. So think about your pounds, and I'm just gonna go 100, okay? 100 pounds would be 400 newtons. So when we do problems and it talks about triple digit newtons, it's okay. If you're in the thousands, it's okay, because it's a big number, okay? I think it's 4.4, but I can't remember. You're not going to see pounds on AP exam. It'll all stay newtons, okay? All right, so if an object has mass, which all 100% of our objects will have mass, it's going to have weight. It's going to have a gravitational force. Yes? About what? Mass versus weight? Yeah. Sure. Sounds like a good idea. Yeah, somewhere along the way, you'll have to know the difference. It may not be, what is the difference between mass and weight? It might say, here's a 5 kilogram object, go find the tension force. But to find the tension force, you have to use the weight. To know the weight, you got to multiply mass by 9.8. And so you'll have to know how to apply it. Okay, contact forces. I mean, theoretically, you could come up with 100 different contact forces, right? The force of the chair, the force of the table, the force of the ground. But what do they all have in common? They're all a surface. And so the first contact force I'm going to put down, you might think surface force. Nope. It's called a normal force. And so that picture I showed you earlier, Fn, is a normal force. Okay, Fn is a symbol, a symbol. It's not the only symbol. So again, depending what video you watch, depending on who wrote the question, you could also see just a capital N. And I really don't like this one because I've already written a capital N and told you it was what? Newtons. There's a difference. Newtons is outside of a number. It's a unit. This capital N is a variable for normal force. I personally don't use it, but again, you might see problems. Even on the May exam, College Board contradicts themselves, okay? But it's normal force. So what is a normal force? It is a force due to a surface, and you draw the normal force perpendicular to the surface. By the way, if you're saving room, I'm going to have 4 main contact forces. So I'm trying to leave myself 4 rows. Perpendicular. In math, when you see the word normal, normal to the plane, they're actually talking about being perpendicular, okay? We'll draw some examples here later on. The second one also comes from a surface. What if I take a box and I slide it across the surface? Well, depending on the surface, maybe it's this concrete floor, it's going to come to a stop, yes? Why? What force is causing it to come to a stop? Friction. And so we've got this frictional force. Now, Miss Earhart prefers a capital F and then a subscript F. Again, I like all my forces to start with a capital F. But even on, do you mind getting it? Even on the AP exam, they may not write capital FF. They might just write a lowercase f. And I really don't like this one. Again, I told you, College Board just needs to make a unanimous decision. Look at the formula chart. Find little f in the legend. On the College Board formula chart, what does little f stand for? Frequency. Now, we haven't studied that yet, but it's not friction, right? So the formula chart only gets you so far. You got to be smarter than it, right? Okay, so when it's a force problem and you see a little f and it's, directed and you want to call it friction, it's probably friction. It's not frequency. Okay. Now, friction might take up 2 rows here. We have 2 kinds of friction. We have gripping friction, and slipping friction. Now, later, when we get nitty-gritty for the second exam, we'll call these different things. But here in the beginning, if you think about 2 objects in contact with each other, go back to that box that we slid across the floor. It's sliding, it's slipping. What kind of friction specifically slows it down? Slipping friction. It's resisting that motion, yes? Okay, so this is like a box sliding on the floor. So what about gripping? Now, I wish I had planned ahead. Imagine I have this board and I put the box on the board and I'm going to lift it up, like this. I'm making an inclined plane, okay? And so, but the box isn't moving. Why not? If the box doesn't move, there's some kind of grip with the board, right? And so that gripping friction kind of holds it in place, okay? So it can hold it in place. And I'm using examples that we're going to see in our diagrams here in just a second. But there's actually another cool example for gripping friction. Now, if you're watching the video, I'm going to walk away from the computer for a second, but watch me walk. How do we walk? One foot in front of the other, right? I'm going forward. Am I an object? Yes. So we're going to break down walking, okay? AP, we're going to break down walking. For me to walk forward, there has to be a net unbalanced force on me. Something's going to push me forward. Can I push myself? No. If you're thinking yes, you're pushing off the floor, let's break it down. It's in that back step. That's what's going to propel me forward, yes? The back step. Who do I push when I walk? The floor, the earth, the surface. That's not Earth's gravity. I'm not pushing on Earth's gravity. I'm literally pushing on the surface, right? I'm pushing back. Now, if I'm wearing the wrong shoes or the right shoes on the wrong surface, if the surface is icy, can I walk the same way? When the floor is icy, there's less friction, less grip between my shoes and the floor, right? And so here's how you walk. You ready for this? I push back on the surface, and the grip between my shoes and that surface, the friction, gripping friction, push me forward. Yes? Without friction, would I be able to walk? Would our car tires be able to grip to turn? No. And so friction, gripping friction, can actually be for walking as well. So it doesn't have to be with a stationary object per se. Okay, it could be, but it's not only. And so one more thing I want to add to friction there is that it's parallel to the surface. And so if you noticed, I was saying the words forward and back. I push back on the surface, and then the grip with the surface pushes me forward, okay? And so it's parallel. And so normal force and frictional force might both be present if you have a surface, but be careful, one is perpendicular and one is parallel. Yes? So in that example, I don't know the mass of the floor, right? That's kind of never ending if you include the ground, right? And so in that sense, we can also apply Newton's third law to walking. So watch me walk. I am one object, I push on the floor, another. That same floor pushes back on me, equal and opposite. So if I want to walk faster, I need to push more, right? Don't you push off on the ground more? Think about runners accelerating, right? Okay. And so I don't know the mass of the floor, but using Newton's third law, I could use my mass, right? One that I could easily measure and know that it's an equal and opposite force. So if they want the full force that the floor exerts, or that I exert on the floor, I really just have to find the force I exert on the floor, and then it's equal and opposite. Right? Okay. Who knew walking could be so complicated, but walking, gripping friction, and that's an example of Newton's third law. Okay, two more forces. Let's get them in there. Okay, if you look at the other pictures down below, some of the objects are held with a rope. Does anyone know what kind of force we say that ropes and strings and cords and lanyards have? Tension. So tension force. And if you haven't caught on, Miss Earhart labels it F subscript T, and not on purpose, but sometimes I do a capital T, and other people sometimes use a lowercase t. That's okay. And then again, I'm going to complain about College Board not being consistent. On the May exam, and some in your packet, NIMSY too, they might use a capital T for tension. And you're like, okay, no problem. Look on the formula chart that you're given. What does capital T stand for? Period. Now, we haven't learned about period yet, but it's not tension. And so here's every year a student's like doing a tension problem, and it says, what is the tension? And they say, Ms. Earhart, is this the equation for tension? And they point to the T equals on the formula chart. No, that's period. Well, where's the equation for tension? It's not on there. We make our own, and I'll show you how we do that probably next class. But the tension equation is not on the formula chart. The normal force equation, not on the formula chart. And so tension, how do we draw it? Well, if I have a vertical string, it's going to be a vertical force. So it's going to be parallel to the string, but do strings push or do strings pull? They pull. And so the string tension force pulls parallel to the string, cord, rope, okay, whatever your favorite type of string is. Okay, so it pulls parallel to the string. They don't push. You'd have to have like a rod, a beam to push, right? And then the fourth common one, we define force as a push or pull. So if I am an outside force, if you will, to an object, and I push or pull it, it's called an applied force. An applied force. And I usually say FA, and then this is sometimes on the AP exam, they just say, you apply a force, comma, F, a capital F. And you're like, what kind of force? Well, they say in the words, an applied force. Usually when I do the AP problems, I still do my own way. And I promise you, enough AP teachers do capital F and then a label that it's going to be okay. You can use any of these. You don't have to use exactly the N, the W, the T, that all represent something else. And so this is just a push or pull. Push or pull. And you can push something parallel, you can push something perpendicular, right? Okay. And so we got a few more minutes. Let's see if we can get the first two drawings done, just two. Questions on our types of forces. You can think of it as kind of a list for the diagrams we're about to draw. Okay. So on the left margin, I'm actually going to put a couple of things that, if you look at AP rubrics, there's some rules to draw in force diagrams, okay? First of all, I've been hinting at it, arrows. If you draw lines and do it perfectly, but you don't have an arrowhead, no points for you. It's a vector. Force is a vector. You have to use an arrow. And then most force diagrams, when we get to rotation, things will change a little bit, but most of the force diagrams you'll see in your book, on this packet, on AP Classroom, you're going to draw from something we call the center of mass. And we have a whole lesson about center of mass later on. For right now, we'll just say it's center of object. It's not always true. If you think about a broom is one side heavy, right? And so the center of mass is not in the center, it's closer to wherever the heavy side is. But for right now, all these boxes you see, we're just going to say the center of mass is in the center of the object, right? And I just put a red dot on those boxes. And that's actually what you'll see on the AP exam. When they want you to draw a force diagram for points, by the way, you can always draw one even if they don't ask you to. I always draw a force diagram, okay? It helps the physics. But you just see this dot, and that's supposed to represent the object's center of mass. And notice I said draw from, okay? We don't draw with the arrowhead pointed towards the center of mass. You draw from the center of mass, okay? Does that mean if you draw it to the center of mass, you'll lose all the points? No, you'll probably get some of the points, or maybe the way they grade it, you'll still get all the points, but this is just the norm, okay? So what about an object that lies motionless? That's another way of saying it's at rest. Well, objects at rest remain at rest until tomorrow when we push it. Y'all, the other rule for force diagrams, they are just snapshots in time. Just because an object is motionless today doesn't mean it's motionless tomorrow or even 5 minutes from now, right? You're motionless right now, and in 6 minutes, you're going to skedaddle. You're going to be in motion. You're going to accelerate, right? Gripping friction, you're going to run, right? No. So they're just snapshots in time. And so object, well, it has mass. They don't say it, but every object has mass. So every object is getting pulled by gravity. And so gravity is pulling you towards the center of Earth, which from a piece of paper frame of reference, it's going to be down. And so I'm going to put a down arrow, and you have to label it with the correct force, okay? And so I'm calling this FG, and it's a subscript, not F times gravity. No, it's a gravitational force. What else? Oh, no, I'm not doing number 2 yet. You're jumping ahead. Let's finish number 1. What other force is acting on this object for it to remain motionless? A normal force. It's just sitting there, right? And so even if it's a hockey puck on ice, it's just going to remain there. But there's a surface, and that surface is going to provide a perpendicular normal force. So if it's a horizontal surface, what direction is the normal force? Vertical, and it would be pushing it up. And so Fn. True story, if you use a W and a capital N, AP does accept that. As long as you know it's not work and Newton, it's normal and weight. Now, these two, if you're motionless, they should be balanced, right? Balanced forces. Which of Newton's 3 laws deals with balanced forces? The first law. So I'm going to put Newton's first law. That's what this is an example of. And so Fn is going to equal Fg. So here's the one from the meme earlier. Fn and Fg, they're equal and opposite, but they're acting on one object. Is it an action-reaction pair? No. And so just note to self, not an action-reaction pair. Okay, not an action. It's not Newton's third law. They are equal and opposite, but not Newton's third law. Number two, if this was a quiz a week from now and all I had you do was draw diagrams, 70% would miss number two. Okay, and if we had more time, I would say, go try it. But let me show you a video first. It says the object slides. Present tense. Was it once hit? Sure. Oh no. Remind me and I'll show you the video. It's a hockey puck, okay? On Friday. Y'all have a great Wednesday.